The next talk is by Sunil Sake. The title is York Slicing in JT Gravity. Sunil.
So let me begin by acknowledging the organizers for giving me the opportunity to present my work here. So this is some work, ongoing work. The talk is based on the ongoing work with Onkar, who is also present here. As the title of my talk says, York Slicing in JT Gravity. I'll be mostly talking about the gravity part of the conference here, trying to conserve the nature of topics. A lot of people have talked about information and field theory. Okay, so let me begin with a very mandatory slide on JT gravity. JT gravity, I'm sure most of you have heard about it. It's a very simple two-dimensional model of dilaton gravity, and it arises universally in the near horizon limit of a large class of black holes in the S-wave reduction. It is a very simple theory, almost trivial, with no local propagating degrees of freedom in the bulk, and most of the dynamics is just encoded entirely in the boundary. If you take the asymptotic limit where dilaton and length of the boundary scales in a certain way, the boundary action is just Schwarzschian action. But the most important advantage of this model is its simplicity, owing is the analytical tractability, which leads to the advantage that one can compute a lot of quantities exactly. Okay, and due to this, it has proven to be a very useful toy model and has led to some novel insights in various problems. Some of them are this black hole information paradox, understanding of ADS to CFT1 dictionary, interesting connections to random matrix theory, questions related to gravity path integrals and second order formalism, and even those tied to cosmology, for example, in de Sitter statistics. So given all these advantages, I will try to make use of this model to do some computations and present some simple results. The broad outline of my talk is as follows. I will just begin with a setup of JT gravity, motivate the problem that we want to study, and it will be related to studying JT gravity in the presence of non-smooth boundary conditions. So I will explain what kind of boundary conditions that I'll be interested in today's talk. And then once I make clear this set of boundary conditions, then we will try to compute the wave functions of JT gravity with these kinds of boundary conditions. Having done that, I will present some checks on these wave functions and end with some conclusions. Okay. So let me begin with just giving the setup of JT gravity. As I mentioned, it's a simple model of 2D dilaton gravity, which involves just two variables, the metric and the dilaton. Okay. Here phi is a scalar field dilaton, and the metric is G, which R is Ricci scalar, and there is a boundary term, which is a usual Gibbons-Hawking boundary term, which is required for a well-defined variational principle. If one works with the boundary conditions that dilaton and metric are held fixed at the boundary. Lambda is a cosmological constant. For the talk today, I will set it to be equal to minus 1, so that we are working in ADS space. The model is so simple that one can immediately derive the equations of motion for both the metric and dilaton variables. The dilaton equation of motion sets are equal to -2, which is locally ADS space-time. The equation of motion obtained by varying the metric is slightly more complicated, but it gives an equation for dilaton which can again be solved completely, and it's fairly straightforward. Now one particular solution is a global ADS solution which has the line element of this form, where the in terms of these coordinates r and t, and the dilaton here is proportional to the, we can take it to be proportional to one of the coordinates r. No, for most, the whole talk is without matter. I will not add matter. Okay, so if you notice slices of constant dilaton, which is r equal to constant, are time-like slices. Whereas if you compute the extrinsic curvature of slices of constant extrinsic curvature are spatial slices. So extrinsic curvature slices are one potential choice for the choice of time in this Lorentzian theory. And the slices of constant extrinsic curvature are referred to as York slices in the literature. So today's talk will be mostly about these kinds of slicing. And now we want to compute wave functions in Lorentzian theory with the appropriate boundary conditions that I'll mention by using Euclidean path integrals. More specifically, the kind of wave functions that I want to study today is those where the extrinsic curvature is fixed and the length of the boundary is fixed, length of the slice is fixed. These are, to compute these wave functions in the Lorentzian theory, we'll do Euclidean path integrals, where part of the boundary is asymptotic, where the boundary conditions are that dilaton and metric are held fixed, and part of it is York boundary, where extrinsic curvature and the length of the boundary are held fixed. Yeah, I'll come to that. Yeah. Okay. One interesting observable that is studied in this JT gravity setup is the usual Hartle-Hawking wave function, which is the one where part of the boundary is this asymptotic boundary where dilaton and the metric is induced metric on the boundary is held fixed, and the other one is a geodesic boundary which has extrinsic curvature k equal to 0 with some length. Okay. However, the dual interpretation of this observable in the matrix model is not fully well understood. I think Adam is going to give a talk about this later this week, and but in today's talk I'm not going to talk about the matrix model interpretation of these, but rather what I'm going to do is to study another interesting class of observables where instead of these geodesic boundaries, we will have part of the boundary to be asymptotic and part of the boundary to be a extrinsic curvature boundary where the extrinsic curvature is non-zero but some constant value. Okay. And this requires studying JT gravity with non-smooth boundary conditions. In particular, the non-smoothness is because of these corner points, because the boundary conditions at these points are different from the different boundaries. One thing I have to emphasize here is that these boundaries are located in the asymptotic region, so that there exists a well-defined dual matrix model observable for these kinds of wave functions. Okay, let me just briefly mention what is already known in the literature. The one well-studied quantity in the literature is the one where the full boundary corresponds to one single particular set of boundary conditions, which is the dilaton being held fixed and the induced metric held fixed, which is in effect the length of the boundary being held fixed. Okay. And this path integral can be evaluated in the limit where dilaton and length go to infinity with the ratio held fixed. Okay. This has been computed by various people, including one in which I am involved. And the answer looks something like this, where there is an on-shell piece which is coming from the Schwarzschian action, and there is a one-loop determinant around the Schwarzschian action, which is the this 1 over beta to the 3 half. Okay. And one can write a spectral decomposition of this answer in like this, which shows that the density of states is some sine hyperbolic function. One can also see that this partition function, so this has been computed by adding an additional counter term to the usual JT gravity action, and if you take that extra contribution from the counter term, one can see that this full partition function satisfies a Wheeler-DeWitt equation in terms of this L and phi variables. Yes, if you do radial quantization, this is exactly. Yeah.
And this is the unique solution to that?
No.
The form above?
No.
You cannot solve it and show that it has to have this form?
No. Path yeah. This is one of the solutions, but this is not the only solution for this.
There are other solutions?
Yes, yes. Yeah, I will come to those things later. Okay. So now this is a smooth boundary condition, but what we are interested in is one where we want two different kinds of boundary conditions on both two boundaries. So we have to study the problem of non-smooth boundary conditions. So let's go back to the ADS action and try to understand what the non-smoothness corresponds to in the variation. What are the appropriate boundary terms that we need to include for a well-defined variation? So if you take the bulk part of the JT action and vary it, the boundary terms that you get up to equations of motion are these two. Is this boundary term, where this is on a codimension 1 slice. You can see clearly from here that extrinsic curvature is conjugate to the dilaton, and the metric is conjugate to some combination of extrinsic curvature and the normal derivative of dilaton. The important piece here is this extra term, which is a corner term, which arises when you have two different types of boundaries and which are non-smooth, which are not same. So this corner term is a codimension 2 term, and it's at the location where the two different types of boundaries meet. Okay. So the various kinds of so all the possibilities that we can study in this model are listed as here. You can have either full smooth boundary, which is dilaton and induced metric held fixed, for which you will need a Gibbons-Hawking boundary term. Or you can just have a full boundary where extrinsic curvature and induced metric is held fixed, for which you will not need a Gibbons-Hawking boundary term, because if you just go back to this, look at this, if induced metric and the extrinsic curvature are held fixed and there is no second boundary, the whole boundary is just one type, then the boundary variation, this variation term will identically vanish, so you don't need an extra boundary term. The other possibilities that that is of interest for us in today's talk is the last two cases, where we have part of the boundary which is dilaton and induced metric held fixed, and another part of boundary where extrinsic curvature and its induced metric is held fixed. This is the case 3 here, and for that we need a Gibbons-Hawking kind of boundary term on the asymptotic boundary slice here, and a corner term at these corners, and this extrinsic curvature slice doesn't require any boundary term. Or you can have both boundaries which are of extrinsic curvature type York boundaries, for which you don't need a Gibbons-Hawking boundary term for each of the boundaries, but you'll need a corner term at the corners because the extrinsic curvatures are different.
From the point of view of the Wheeler-DeWitt equation, how would these boundary conditions, how would the equation differ? How would you put this in?
Yeah, so for each of the Wheeler-DeWitt equation is a local equation. Okay, so when these are the one I showed here is just a zero mode part of that Wheeler-DeWitt equation. When the boundary when the variables on the boundary, when the canonical variables are the dilaton and the length of the boundary. But if the canonical variables are the extrinsic curvature and the length of that boundary, the Wheeler-DeWitt equation can appropriately be cast in terms of those variables and their conjugate momentum.
You mean there's a representation which is like a Fourier transform? Like there's some representation in terms of the metric, and then there's a conjugate representation in terms of extrinsic curvature?
Yes.
And the question is, at what boundary conditions you put in the wave function in that sense?
Yes.
I see.
I will talk about the Wheeler-DeWitt
So from that perspective, you're not talking about trying to add some terms to the action, but you're just saying you have a wave function and you're giving some boundary conditions for the wave function.
Yes. I will later show, so what I'll do is construct the wave function for these types of boundary conditions and show that they will satisfy an appropriate Wheeler-DeWitt kind. I'll show what the Wheeler-DeWitt. No, it's the same. Yeah, you have to, like for that. Yeah, it's the same Wheeler-DeWitt, but it's slightly different. There is one subtlety because of the corner term, which I'll come to. Theta j is the angle at which you can think of it as the angle between the tangent vectors drawn to these boundaries at the corner. Okay, let me make a choice of coordinate system to work in, which is the one I take is the Poincare coordinate system, and the curves of constant extrinsic curvature in this coordinate system look something like this. There are 3 parameters here: x0, r, and lambda. K is the extrinsic curvature, which is the label for this curve. The quantities x0 and r. First, let me mention that lambda is a parameter that is like the affine parameter along the curve, and the other constants x0 and r depend on the endpoints of the curve. If you say the curve extends between 2 points x1, y1 and x2, y2, that will completely fix x0 and r. Okay, and you can immediately see from these 2 equations that the trajectory, you can see that this from x of lambda and y of lambda, you can see that they follow equation of a circle in the upper half plane. Usually the geodesics are the semicircles in the upper half plane, but these are not geodesics but parts of the circle in the upper half plane intersecting the real axis at some 2 points. And the length of such curve between any 2 points x1, y1 and x2, y2, you can immediately calculate using the parameterization of the curves showed earlier, and it will look something like this. Okay. The point in showing this equation is that if you take the points y1 and y2 to close to the boundary, you see that the length has a particular scaling. If y1 and y2 go like 1 epsilon, the length of this geodesic extrinsic curvature boundary goes like log of epsilon. So the appropriate scaling of various quantities that we would like to consider for evaluating the mixed boundary wave functions is this. Dilaton goes in terms of this epsilon scaling that I introduced. Dilaton goes like 1 over epsilon. Length of the asymptotic boundary also goes like 1 over epsilon, so that the ratio is held fixed. The usual standard Dirichlet boundary condition in JT gravity. And for the other boundary, extrinsic curvature is held fixed to be some constant value, and its length diverges as log of 1 over epsilon. Okay. So the wave functions that I compute will be functions of these data. Okay, let me begin by doing some simple computations. First, let me just show you the on-shell calculation of the wave function just from the value of evaluating the value of the action for these kinds of boundary conditions. For mixed boundaries, where one boundary is asymptotic boundary and one boundary is York boundary, we know if you take the on-shell value of this action, the bulk term doesn't contribute because r plus 2 is 0. So the only contribution comes from the Gibbons-Hawking term for the asymptotic boundary and the corner term at the joining of the two boundaries. It's very straightforward exercise to evaluate both of them. The extrinsic boundary, the asymptotic boundary contribution is proportional to beta, and the corner angle to leading order is in the limit of the scaling that I showed when epsilon goes to 0 is dependent on k, but there is also a subleading. Okay, so you can put these two together to get the on-shell value of the action. Okay. Depends on the runoff, the scaling of dilaton. If you remember, phi, the boundary value of dilaton goes like phi small b. Length of the asymptotic boundary is renormalized length is beta. Renormalized length of the extrinsic boundary is capital L. So it depends on this on-shell wave function depends on all these quantities. Rs is obtained from this equation. So it depends on beta and L. Now let me do a similar computation for the one where we have two York boundaries. Now the contribution here comes entirely from the corner angles. There is no Gibbons-Hawking boundary term. And one can straightforwardly again evaluate the value of this corner angle given the data of the extrinsic curvatures of the two slices and the length of the two slices. It is some tan inverse function of some K1 and L1, another function where K1 just replaces function with K1 L1 going to K2 L2. There are two corners. We have to sum over the corner angles at the two corners, and it will be identical contribution from the other corner also. And the value of wave function we get will be something like this. Okay, now we have computed just the leading classical results. We want to go to the full wave function. The way, so it turns out easier to compute the full value of the wave function for these various boundary conditions using what is known as the boundary particle formalism. Okay. So when we want to do the full quantum evaluation, suppose we start with the path integral, the dilaton integral sets are equal to -2 everywhere, and then we are left with the boundary term. Now we manipulate the boundary term as follows. We use the Gauss-Bonnet theorem, which relates the extrinsic curvature to the Ricci scalar and the Euler characteristic. So this is basically a rewriting of the Gauss-Bonnet theorem, where I have collected the extrinsic curvature and the corner terms on one side and express it in terms of the Euler characteristic and the integral over the bulk manifold of the Ricci scalar. Okay. Noting that Ricci scalar is constant everywhere because of the dilaton integral, this term is just integral over root g, the volume form, and you can write it as a boundary term. Okay. And including the counter term, there is a counter term for the asymptotic boundary. Including that, we see that the action the boundary term in the action, let's say for the case of Dirichlet boundary, ignore the York boundary for a moment. For the case of just Dirichlet boundary where dilaton and metric are held fixed, the boundary action becomes something like this. And this action, where LA is the length of the boundary and integral A is integral of a one form along the boundary. Okay, and this action can be interpreted as a whirlwind action for a particle in an electric field with some specified by this gauge field A. So what we are going to do is to now use this understanding to compute the wave function for various boundary conditions. In particular, let's say for this Dirichlet case, the partition function can be obtained by computing the propagator of this boundary particle with the specified proper length. Okay. So the partition function of the JT gravity with Dirichlet boundary condition with beta being the renormalized length is just a propagator of the particle to travel from a position and come back to the same position in some proper time beta. Okay. The computation of this exact propagator was done by this set of people long back, and what we are going to do is to just use their results and apply it to our case. Okay. The propagator for this particle in the hyperbolic space in the presence of an electric field is this complicated expression, but it will turn out the final answers are not so complicated as they look here, because what we want to do is we want to take the asymptotic limit. Okay. Let me explain some. So here Q is the value of the dilaton at the boundary that enters here. D, the quantity D, is related to the endpoints between which the particle travels. X1, X1. This bold X1 stands for both X1 and Y1 of the Poincare coordinates, and this is the expression of D. First thing we can do is to just check if it reproduces the usual JT gravity partition function, and in the limit of large Q, which is a large phi b asymptotic value of the dilaton, if you take the coincident limit of this propagator where both the points x1 is equal to x2, this quantity D goes to 1, and the hypergeometric function just becomes 1. So this propagator in this asymptotic limit gives the partition function of JT gravity bang on. Okay, now what we'll do is just use this propagator to compute the wave function for the other cases. Let's go to the mixed boundary case. Now we can play the same game that I mentioned earlier of rewriting the extrinsic curvature term and the corner term in terms of an Euler character and the Ricci scalar on the bulk manifold, and doing that manipulation will lead to the boundary action which looks like this. Now there. Yes. Yes. Yeah. Yeah. So the boundary particle action in this case has two terms, one for the asymptotic boundary and one for the York boundary. So the full wave function is then a product of two propagators, the propagator for the asymptotic boundary and the propagator for the York boundary. So we will evaluate each of these in turn. The asymptotic boundary propagator is just the one that I showed before, and all we have to do is take the asymptotic limit of this propagator. Okay. In the large Q limit, there is a nice limit of this hypergeometric function. It will become a Bessel function of some particular order which depends on this parameter S, which is to be integrated over in the wave function, and it depends on D, which was related to the this D is actually related to the geodesic distance between the 2 points, that is this quantity D, and D infinity is just the large asymptotic limit of this quantity D. Okay. So if you take this large Q expansion, the asymptotic propagator, the contribution of the wave function from the asymptotic propagator looks like this. Okay. There is an additional phase factor that has to be kept track of. And now we have to take the contribution from the extrinsic curvature boundary. The extrinsic curvature boundary is a boundary of constant extrinsic curvature which is fixed. So the contribution from this boundary is just the value of this Hornschel term along this boundary. Okay. We just have to compute the value of the Wilson line, along this constant extrinsic curvature boundary, and that will give the value of this propagator. Now we put these two together to obtain the full mixed boundary wave function. Okay. So putting these two together, what you obtain is this. This is just coming from the asymptotic propagator. And further, if we take the large Q limit of this object here, the spectral density, we see that the cos hyperbolic term drops off and we just get sine hyperbolic term. Okay. So that gives the sine hyperbolic term. And this phase factor here from the asymptotic propagator and the contribution of the extrinsic boundary combinedly become this nice object which is just dependent on the extrinsic curvature. Okay. D infinity is related to the length of the extrinsic curvature boundary, renormalized by the dilaton. Okay. It has some nice form. The difference being from the full dilaton Dirichlet boundary case, the only difference is that the presence of this extra Bessel function. Okay. Now I'll show that this Bessel function has a nice interpretation as the energy eigenstates of the Lorentzian theory. Okay. If you take the Lorentzian setup with two boundaries at a constant value of dilaton and take an extrinsic curvature slice of fixed extrinsic curvature and length Lk, the idiom Hamiltonian of this Lorentzian theory, which is a sum of the contributions from the left boundary and the right boundary, if you express it in terms of these variables Lk or its renormalized version, which is L tilde k here, and its conjugate momentum Pk, the Hamiltonian takes this nice form. Now if we ask for what are the eigenstates of this Hamiltonian, one can immediately compute them by promoting this Pk to del k, del L tilde k, and solve for the eigenstates of fixed energy. Okay. That will give rise to this Bessel function, the same Bessel function that we saw earlier, except with the difference that it's 1 plus k square everywhere here as opposed to 1 minus k square that appeared in the Euclidean case. So the Bessel function should be thought of is the analytically continued Bessel function with k going to ik. So this leads to a nice interpretation of our Euclidean results, that what we have obtained. So first of all, this Bessel function is the energy eigenstate expressed in the length basis, length of the York boundary, and the wave function we obtain is just expressing this energy eigenstate which is expressed in the length basis and going from a microcanonical ensemble to a canonical ensemble. Okay, good. So we have this nice interpretation for this mixed boundary case. Now the other boundary, the other one where we have two York boundaries looks like this. Here the computation is even simpler because in terms of the particle picture, the action is just given by this. We have again contribution from both the boundaries with the value of gauge Wilson line along each of the boundaries, and it's fairly straightforward to evaluate this. And just the on-shell value of this is the full propagator because the curve is just one particular curve of fixed extrinsic curvature. Okay. We get the wave function to be of this form, but there is one constraint among all this data. This is a boundary of k1 with length L1 and k2 of length L2, and there is one constraint among all these variables which is imposed as a delta function. Okay, so now what I've showed is how to compute these wave functions for two York boundaries or one York boundary and one asymptotic boundary. So now in the last few minutes, let me show some checks on these wave functions that will turn out to be nice and confirm that what we have obtained is indeed reasonable. The first check that we can think of is, can we reproduce just a classical wave function in the classical limit? Okay. Okay, I don't know how to explain it geometrically, but let me tell you where this constraint comes from. So if you go back to this, when I calculated the length of the curve between any 2 points, you see this object is purely a function of the geodesic distance. Okay, so if you invert this object to express in terms of Lk and k, you can do it for both the boundaries, and both of them the geodesic distance is related to this combination of Lk and k in a particular manner. And it's the same geodesic distance because the boundaries, the slices are between same endpoints. Yeah, yeah. Okay, now to reproduce the classical limit, to check the classical limit, we just have to use some nice integral representation of the Bessel function. And if we use this integral representation of the Bessel function in the mixed boundary wave function, so mixed boundary wave function had this Bessel function, just put in this nice integral representation, and what one can do is do the S integral exactly and do a zeta integral in a saddle point limit. And in that saddle point limit, the exponent that one obtains matches precisely with the classical wave function, classical on-shell calculation that we did earlier. This is for first check. Second check is that we can take convolution of two wave functions that we obtained, two mixed boundary wave functions, and integrate them over the length of the York boundaries. Okay, and that should reproduce the partition function of the JT gravity with full asymptotic boundary Dirichlet conditions. Okay, so we take our mixed boundary wave functions with the Bessel functions, and there is some nice identity involving Bessel functions that makes this happen. Although I didn't show the Bessel function identity, there is a identity which is crucial in getting this right. So what we reproduce is that take two such mixed boundary wave functions and compute the inner product between them integrated over this length. This is just the renormalized value of this length, and you'll end up with getting so the final expression that you get is of this form, where u1 is renormalized, is related to beta 1 and u2 is related to beta 2 linearly. So it reproduces the partition function of the full boundary with the fixed value of dilaton. Okay. One other convolution one can think of is take the mixed boundary wave function and convolve with the one where we have two York boundaries. Okay. That should give the wave function where the York boundary is replaced by where this Lk and with extrinsic curvature k is just replaced by L tilde k with extrinsic curvature k tilde. That also owing to this delta function constraint happens straightforwardly, and we get the correct mixed boundary wave function with the correct value of new extrinsic curvature and new length. Okay. Okay, the last check that I wanted to talk about is the constraint equations. Okay. Yes, you can take two York boundaries. I mean, you can take two York boundaries and take the convolution, and that also works. It will give a third two York boundary case with two different extrinsic curvatures appropriately. So the third check that I'm going to do today is the constraints. What we want to check is if the wave functions that we constructed satisfy these constraint equations. What I mean by constraint equations is the Wheeler-DeWitt equation when we write the metric in the ADM gauge like this, radial quantization. So the local Wheeler-DeWitt equation looks something like this, that is obtained by varying the action with respect to the function n here. This is a standard well-known Wheeler-DeWitt equation. Now we want to check whether this promoted to an operator annihilates the wave functions that we constructed. Okay. For the asymptotic boundary, the dilaton and the boundary metric are held fixed. So the data there is the canonical variables there are the dilaton and the induced metric on the boundary. The corresponding conjugate momenta are these two quantities. For dilaton is the conjugate momentum for dilaton is the extrinsic curvature, and the one for the induced metric is the normal derivative of dilaton. Now if you express the Wheeler-DeWitt equation in terms of this canonical momenta and the variables dilaton and the induced metric, it looks like this. Okay. Now if you take the zero mode part of this, for smooth boundaries this term drops out because this d here is a covariant derivative along the boundary. Covariant derivative with respect to the induced metric on the boundary. Okay. Yeah, along the slice. Uh, so this is just coming from the action. Yes. Yeah. So usually if the boundary is totally smooth, this term is unimportant because this is just a total derivative term when you integrate it along the boundary. And if the boundary is a smooth boundary, full smooth boundary, this term doesn't, because it's a total derivative, it vanishes. You're saying this term is always there? It's always there, but it's not important when the boundary is totally smooth. Okay. But when the boundary is not smooth and you have some corners, this term is important. But for the asymptotic boundary, this is still unimportant because the boundary term that you get looks something like this, where r here is the tangent vector to the boundary, asymptotic boundary. So this is like a tangential derivative to the boundary. And since the asymptotic boundary is the one where dilaton is held fixed, the tangential derivative of the dilaton should vanish. So for the asymptotic boundary, the Wheeler-DeWitt equation is still not modified. And you can check from the mixed boundary wave function that this is indeed true. And this operator annihilates the wave function. But for the York boundary, again, one can compute the conjugate momentum and the induced metric along the boundary and express the Wheeler-DeWitt equation in terms of these two quantities and the extrinsic curvature and also the induced metric. Here again, we will have an extra corner contribution. And this corner contribution is now important because this quantity acting on the wave function will give some non-zero result, and that is exactly cancelled by the corner contribution coming from the corner. Okay, so these are the three checks that I wanted to discuss, and so the punchline is that the wave functions we computed satisfy all the three checks, including this modified Wheeler-DeWitt equations. Okay. That almost brings me to the end of my talk. So let me just summarize. What I've shown is that it is natural to use York time in ADS, and the wave functions specified by constant extrinsic curvature can be constructed from Euclidean path integrals. So we constructed wave functions corresponding to more general class of observables, where the part of the boundary is non-geodesic boundary but of a fixed extrinsic curvature. Okay. And we carried out some basic checks of the wave function, matching with some of them being the on-shell matching with the on-shell calculation, and taking the appropriate convolution to give the expected results. And we also showed that the wave function satisfied a modified Wheeler-DeWitt equation where the corner terms play an important role. Let me just end with some open questions. Okay, we computed the mixed boundary wave function with York boundaries in this boundary particle formalism, but we haven't yet fully understood it, how to compute it directly in the second order formalism. So that is one thing that one can think of. And also the mixed boundary wave function and the York boundary wave function, we have computed with the corners being in the asymptotic region. One thing one can do is to consider the corner point somewhere at finite location in the bulk and try to see how these wave functions get modified. Also, one other open question is this: how this modified Wheeler-DeWitt equation can be understood as a modified TT bar equation for the boundary theories. The last one is what is the relation of our work to Cauchy slice holography that people have been thinking about, including Onkar. Yeah, that's it. Thank you.
Perturbatively in higher dimensional ADS.
Yes.
And there, in fact, we did find solutions including matter. And of course, we are working in perturbation theory, but since you're working in JT gravity, maybe you can go beyond that. But it shouldn't be so hard to solve the full equation including matter, right? You'll get a matter wave function and then you'll get a dilaton wave function that...
I suppose it's possible, okay, but we haven't...
I see. You know, an interesting thing we got from that was we could prove the following result. We could prove that two solutions of the Wheeler-DeWitt equation that coincided at the boundary had to coincide in the bulk. So that was like some perturbative version of, you know, or version of holography, but proved by using this. And here maybe you can prove this exactly by, you know, you can show that two solutions that coincide at the boundary must coincide in the bulk. That would prove that, you know, theory.
Yeah. Yeah.
Yeah.
Yeah.
That's in the future.
There's a model for ADS also.
So just ADS, but it is on the radial equation.
You do the exact path. Conformal matter you can do. That's no.
Maybe we also want to see the Lorentzian set rather than doing the Euclidean part. You see, the thing you're talking about is what will continue to the decision problem. But what about solving the Lorentzian thing? Then it's slightly, you have so many pocket sizes in ADS. And that's not been done.
Yeah.
So one could prove this result about that, but it's
Not as easy.
Yeah, it was.
yeah, no, it's not as easy. But
Yeah. 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 I wanted to put it as an open question, but somehow. Yeah.
Okay, there are no further questions. Let's thank Sunil. Let's thank all the speakers.